Okay, the next screencast in this series on sequences and series is on sigma notation and arithmetic sums. So far we've looked at arithmetic sequences and we've looked at geometric sequences, and we have established that for an arithmetic our nth term, or un, is equal to the first term plus 1 less the number of terms times d. And for a geometric, we have established that our nth term, or our un, is equal to u1 by r to the power of n minus 1. Okay, so that's where we're up to. Now we're going to have a look at summing a sequence, which is called a series. And we'll look at that in a moment. But first, I'm going to introduce this sigma notation, which can look a little bit weird, or does look a little bit weird, I suppose. But we're going to understand it by having a little look at it now. Sigma notation is basically a short form of expressing a sum, or a shortcut of expressing a sum. So let's have a look. Right, so we use sigma notation, uses sigma, and the capital Greek letter sigma looks like that. The lowercase looks like that. But the uppercase, and in mathematics we use it as a symbol to denote that we're talking about the sum of. Now, let's say we're going to talk about the sum of the terms n, where n goes from, right, let's go the other way. Let's say we've talked about it being a shortcut. Of expressing a sum? So let's have a look at a sum. It goes on for a while, because there's no point having a shortcut for a sum that goes 1, 2, 3. We don't need a shortcut for that, but we sure do if we want to express a sum that goes from 1 to 100. Okay, so how would we do that? Well, this is how we do it. We use sigma notation. We establish how many terms there are, the starting point and the finishing point. In this case, that's 1 and 100 of an expression that, once we substitute these values of n in, will turn into these values here. So this is equal to 1 plus 2 plus 3. Now let me explain. So what we do is we substitute these values of n into this expression here. Now that expression is a very simple one at the moment, it's just n. So we sub n equals 1 in there and we get 1. We sub n equals 2 in, we get 2. So we substitute 100 different numbers in for n. We produce 100 different numbers here, and the sigma says sum them, add them all up. So this is the shortcut to that. They are equal. Obviously, one is quicker to write than the other. Let's say we want to have a look at, let's say we wanted to have a look at 3 plus 5 plus 7 plus 9, and we wanted to do this, and we wanted to go all the way to, I don't know, 151. Now, if to write that in sigma notation, right? So that in sigma notation, what would that look like? Well, firstly, we need to know how many terms there are. So we could actually now go in and use what we know about the nth term and find out what 151 is equal to. So we go say un, we don't know what n is. The first term is 3. It's an arithmetic sequence, isn't it, with a common difference of 2. So n minus 1 by 2. And we know that nth term is equal to 151. So now if we solve this equal to n, 3 plus 2n minus 2 equals 151. Remember what we're doing here, 2n is equal to 150, so n is equal to 75. What that tells me, therefore, is that there are 75 terms in this sequence. So in sigma notation, okay, in sigma notation, we're going to go from n equals 1 to 75, because there are 75 terms, and now I want an expression here that's going to pick up each of these terms. Now, if my common difference is 2, which it is, then it's a 2n linear expression. Linear, importantly, a linear expression, a sum of linear expressions results in an arithmetic progression or sequence. A linear expression here results in an arithmetic sequence. So 2n, and what do we need to do? 2 times 1 is 2. I need to add 1 to that. Let's just check that. When you put 1 in there, you get 3. When you put 2 in, you get 5. Put 3 in, you get 7. When you put 50 in, you get 101. When you put 75 in, you get 151. So that is my expression for that sum. So just importantly, pick up that note there, that a linear expression here will equal an arithmetic progression. And if that happens to be exponential, then it will be a geometric. So I'll show you, let's have a look at an example here. The sum from n equals 1 to 10 of 3 to the power of n. Well, that's equal to, let's do it now, 3 to the power of 1, 3, plus 3 to the power of 2, 9, plus 3 to the power of 3, 27, 3 to the power of 4, 81. You see what's going on here? Now we've got a common ratio of 4, so what we've got is a sum of 10 terms of a geometric that has a common ratio of 4. So what we've got to note here is that when this is an exponential expression, then we will get a geometric sequence. Or, it's a sequence, but because we're looking at the sum, then we'll say it's a series. Remember, a series is a sum of a sequence. Okay, the chapter's heading is sequences and series. Series are just the sums of those sequences that we've been looking at in the first couple of YouTubes. Okay, so that's sigma notation. And now we want to have a look at some arithmetic sums, which are called series. So let's now put down a little heading here, arithmetic series. Remember that word there just means sum of the sequence of arithmetic numbers. Okay, so let's have a look at an example and go from there. Nice little story to kick things off here. If we have a look at the most basic arithmetic sequence or series of all, 1, 2, 3, 4, all the way up to 100, if I was putting this in sigma notation, which we'll do in a moment, 98, 99, 100. If I was putting that in sigma notation, I would write it as n equals 1 to 100, n, linear function, arithmetic sequence. Okay, this challenge was given to an 8-year-old German student in the 1700s. His name was Carl Friedrich Gauss, G-A-U-S-S. Became a very prolific, famous mathematician. As an 8-year-old, he was given this as a task, I think, to shut him up. He was being a bit naughty in class. So he was given this task. His teacher set up the numbers from 1 to 100, hoping to occupy him for some time. Gauss just ripped out the answer, 5,050, in no time. He just said, that's the 5,050. Next question, please. How did he do it? Well, this is how he did it. How did he do it so fast? Well, if we have a look at pairing this up, let's have a look at the first term and the last term. We want the sum of this, all 100 numbers. And if you just have a look here at these pairs of numbers, what do we find? 596. We find, if you look at them, they all add up to 101. And if you think about why that is the case, then as we go up by 1 here, we go down by 1 here. So whatever this is here, this will be our D, our difference. We're going down by that difference each time from the right as we go up from the left. So we're always going to have, in an arithmetic sequence, pairs of equal sums. So all our job really is just to find out how many pairs there are. Now in this case, there are 50 pairs of numbers that sum to 101. So all Gauss had to do was work out what 50 times 101 was, and he worked out 50 times 100 is 5,000. Just chuck another 50 on top, That's 5,050. That's how he did it. So what does he use? So let's look at the formula then. If we're going to, so the sum to n terms of an arithmetic sequence, well, what we're saying here is if there are n terms, then I just need to halve that number. So here, the 50 pairs. There's n over 2 pairs of the first term plus the last term. First term being u1, here it is as 1, and un is the nth term, in this case 100. Now we haven't always got this un number, so what we're going to do is we'll come up with another formula, because we know that un is equal to the nth term is u1 plus n minus 1 times d. So if I just replace un by that, if we insert that back in here, we will get another formula which is sometimes more useful. So u1 plus this here, so we end up with 2u1 plus n minus 1 times d. So they're our formulas to work for to find the sum of an arithmetic for us. So let's have a look at an example. Okay, first example's on the screen. Suggestion is that you have a go at that yourself. Now pause the video and have a go, just using this formula here for the sum. Now, all right, hopefully you've had a go at it. This is, so our sum to the first 15 terms. We want 15, S15, n equals 15. Right, now n over 2, so we've got 7.5 terms. I don't know what my last term is. You can go and find it, or you could just use this second formula here, which doesn't need the last term. It just needs the first term, which is 29. So 2 times 29 gives me 58. 2 times 29 plus n minus 1 is 14. And d, well, we're going down by 8 each time, aren't we? So d is minus 8. So I just need to work out here what's 7.5 times 15 plus, I'll get the calculator. Right, I've got the calculator out. 7.5 times 58. So I just need to put 58 plus, was it 14 times minus 8 in there? Minus 8 was my common difference. Hit enter. Minus 405 is our sum. Minus 405 is a minus out the front there. There's our sum of 15 terms. Okay, next example. Okay, in example 2, find the sum of the following series. So in this case, we've been given a series we need to establish. Looks like it's a arithmetic going up by 1.5. Yes, 1.5, 1.5. That all checks out. Now we know the first term here. We know we've got u1 here. We don't know what n is, but I do know what my last term is. Okay, so my last term is 50, which is un. So we just need to work out what un is first. What n is first, and then we can go and find the sum. So I know that un is equal to u1 plus n minus 1 times d. Now in this case my un is 50. So therefore my u1 is 14. So I can go 14 plus, I know d is 1.5. So I can go 1.5n minus 1.5 is equal to 50, and I can solve this for n. So I've got 1.5n here equals 50 plus 1.5, 51.5 minus 14 is 37.5. And therefore n is equal to 37.5 divided by 1.5. 37.5 divided by 1.5, 37.5 divided by 1.5, that's 25. So that means I've got 25 terms. Now I just need to find the sum. I've got 25 terms. I know the last term and the first term, so I can use the first formula. That's n over 2, 25 over 2. First term 14, and last term 50. Remember, that is my 14 plus 50, 64. I've just got 20. I've got 12.5 pairs of 64. So 12.5 times 64. Go in here, 12.5 times 64 gives me 800 as a sum. Equals 800. Okay, that'll do for this screencast. We are now, wow, we're right up to exercise. We can do sigma notation 6F, and we can do some arithmetic series on 6G. So, yeah, let's work on that. See you soon.